Have you ever used your phone to identify a plant just by snapping a picture? Or maybe marveled at how language models like GPT-3 can write poetry or even code? These AI advancements, they feel almost, well, magical, right?
They really do. But, behind all that apparent wizardry, there's a fundamental process, kind of like a beating heart, that allows these incredibly powerful tools to learn and improve.
And that, for you listening, is where our deep dive begins today. We're talking about the backpropagation algorithm, BP for short.
Exactly. Think of it as the absolute critical engine that enables deep neural networks, or DNNs, to actually learn and refine what they do. Without it, these networks would just be static, like complicated calculators, unable to adapt or get better.
Right. So our mission today is to pull back the curtain on this often complex-seeming process. We're going to dive into a really interesting paper. It's called The Backpropagation Algorithm for a Math Student by Damati and others.
And the goal is to unpack its core insights. We want to give you a clear understanding of how these networks figure out what they need to learn specifically, how that all-important gradient of the loss function gets calculated.
Yeah, because you might be using pre-trained AI models all the time, in frameworks like PyTorch or TensorFlow. And that's great.
Absolutely, it's incredibly useful, but truly understanding their inner workings, well, that gives you a much deeper appreciation and, frankly, capability. It moves you beyond just using a black box.
Definitely. You start to grasp the elegant and efficient mathematics at play, which this paper actually illustrates beautifully.
It really does.
Okay, so let's unpack this. To really appreciate backpropagation, we first need to understand the fundamental challenge of training these deep neural networks. What makes it so tough to teach them?
Well, a DNN is, at its heart, just a massive composite function. Imagine like a complex assembly line, right? The output from one station immediately becomes the input for the very next one, over and over again. That's what we mean by composite function of vector-valued functions. Lots of functions stacked together, feeding into each other. The goal, then, is to minimize something called a loss function.
Which basically measures how wrong the network is.
Precisely. It measures how off the network's predictions are, and we make it less wrong by adjusting the network's many parameters. These are essentially the knobs and dials, the weights and biases within each layer.
And this is where it gets really tricky, isn't it? Because these networks are so deep, so layered, and the calculations aren't simple straight lines. Figuring out how to tweak all those parameters perfectly to reduce the error, that's the hard part.
It is calculating the gradient of that loss function, basically, the direction of steepest increase in error with respect to all those parameters. For deep networks, doing that naively is, well, computationally nightmarish.
Yeah, I'm picturing trying to untangle 1,000 strands of spaghetti all at once. It sounds impossible.
And that's exactly where backpropagation steps in. It's the elegant, frankly, indispensable solution. The BP algorithm's main job is just to efficiently compute the gradient. That's its purpose.
Efficiently, that's the key word.
Absolutely. Its genius lies in how it leverages the composite structure of the DNN. It uses the fact that the layers are stacked, and it works backward through the network in a really optimized way.
And this is the real game changer, right? The incredible benefit here is something you should definitely remember, is that, as the paper points out, the number of layers in the network does not significantly impact the complexity of the calculation.
Think about that. You could have networks with hundreds, even thousands of layers, and backpropagation keeps that gradient calculation manageable, efficient.
Wow. Without this, deep learning as we know it today just wouldn't be feasible at scale.
Not at all. Now, this particular paper, Damati et al., focuses on expressing this gradient calculation using matrix multiplication. It employs tools like Jacobian matrices and the good old chain rule from calculus.
Okay, Jacobian matrices and chain rule.
Yeah.
That might sound a bit like diving back into advanced calculus for some folks listening.
Yeah.
Can you maybe give us a more visual idea of what a Jacobian matrix is, for those of us whose linear algebra is a bit rusty?
Sure thing. Imagine you have a function where tweaking one input can actually ripple through and affect multiple outputs, right?
Okay.
A Jacobian matrix is essentially a big table, a map, that shows you all the possible rates of change, all those partial derivatives of every single output with respect to every single input. It bundles all that sensitivity information together.
So it tells you exactly how sensitive the outputs are to tiny changes in the inputs.
Precisely. And the power of this, as the paper highlights, comes from using the chain rule with these matrices. The chain rule isn't just for simple functions. It works beautifully for these compositions of vector-valued functions, too.
Ah, so it lets you break down the derivative of the whole complex, layered thing step by step.
Exactly. Systematically, even with many inputs and outputs at each stage. And what's really nice here, and the paper emphasizes this, is that even though it sounds math-heavy, this approach gives concise mathematical justifications that are actually understandable and useful to a broad audience.
So it's about clarity, making this complex mechanism accessible by showing the underlying elegance even if you don't have, say, a PhD in math.
That's the idea, precision and clarity.
Now, in the real world, many of you interact with these DNNs as pre-trained models. You find them in libraries like PyTorch, TensorFlow.
Which is incredibly convenient, makes them super accessible for developers to just jump in and use them.
But it can also make their inner workings feel a bit, well, opaque, like a black box.
It can, yeah. And think about the sheer variety of DNNs out there that rely on this core process. For computer vision, you've got convolutional neural networks, CNNs, things like ResNet, Inception for classification.
And UNet or YOLO for finding objects and images.
Right. And then in natural language processing, you're looking at these huge, powerful transformer models, BERT, GPT-3, T5, that have totally changed the game for language tasks.
In the training process for all of them, whether you build from scratch or just fine-tune a pre-trained one,
Yeah.
it always comes down to minimizing that loss function, usually with something like stochastic gradient descent, SGD.
Correct. And SGD absolutely requires calculating the gradient of the loss function, so
Okay.
backpropagation. It's foundational to pretty much all modern deep learning. It's under the hood, making it all possible.
Okay, so the paper makes two really key observations that help simplify this whole gradient calculation business, making it much more manageable. What's the first one?
The first observation is actually pretty clever. It points out that you can look at the overall loss by sort of separating the last layer activation function from the rest of the network.
So instead of tackling the whole thing at once, you kind of isolate that final step first.
Exactly. It simplifies the view, like focusing on the end of the assembly line before worrying about every single station before it.
Okay, that makes sense. A classic divide and conquer approach. And the second observation.
The second observation connects the Jacobian directly to the gradient. For a function that just outputs a single value, a scalar-valued function, its gradient is simply the transpose of its Jacobian matrix.
Okay. So they're like two sides of the same coin, just different ways of representing how the function changes.
Pretty much. It gives us a direct mathematical link. And the advantage of putting these two observations together is huge. They allow the original, really complex gradient calculation to be separated into two distinct calculations. Makes it much easier to handle.
And the second part of that calculation, the bit involving the loss and that last activation function, the paper says that's surprisingly straightforward because the choices aren't random.
That's right. In practice, people use standard combinations. The paper gives a helpful table, Table 1, showing these. For binary classification, predicting one of two things, you typically use a sigmoid activation with binary cross-entropy or BCE loss. For multi-class classification, picking one from many categories, it's usually softmax activation with cross-entropy, CE, loss.
Right.
And for regression, predicting a continuous number, it's often an identity function, basically no activation paired with square error or SC loss.
And the punchline.
The punchline is that for these common pairings, the authors show that the gradient of the loss with respect to the input of that final layer, what they call SEL, can be calculated very, very simply. Like for CE and BCE loss, it often boils down to just the negative difference between the true value and the prediction.
Wow, so that cuts down a huge chunk of complexity right there.
It really does. It simplifies that second part of the separated calculation enormously.
Okay, so we've broken down the problem conceptually, simplified the last layer. Now, how does this actually work step by step when we're calculating gradients across multiple layers? Let's start with the basic building block, a one-layer network.
Right. The single-layer network calculation is foundational. The paper makes the point that this simple one-layer network can actually be seen as a model for the last layer of any deep neural network.
Oh, interesting.
Think of a simple case. Say 4 input features, and you want to classify into 3 categories. Your network needs weights connecting each feature to each category, plus a bias for each category. That's, 4 times 3 plus 3, 15 parameters already,
That's for one layer.
just for one layer. But we can calculate the gradients for all 15 efficiently using our Jacobian approach and those simplified loss gradients we just talked about from Table 1.
Okay, but as you said, one layer often isn't enough. Performance usually improves with more layers. So how does backpropagation handle adding, say, a second layer?
This is where the iterative nature, the backward pass, really shines. With 2 layers, you have parameters for the first layer, W1, B1, and the second layer, W2, B2. The calculation applies the chain rule iteratively.
Working backward.
Exactly. It calculates the gradient needed for the second layer's parameters first. Then it uses the chain rule to propagate that error signal backward to figure out the gradients for the first layer's parameters. It links the required adjustments across layers.
So it's a systematic, step-by-step backward flow of information about the error.
Precisely. Highly structured and efficient.
And this idea just keeps going no matter how many layers you add. The paper uses a 3-layer network example, Lynette 100, 310, a classic image classifier, to show this, right?
Yes, it generalizes perfectly to an arbitrary number of layers. For Lynette, you might feed in a flattened 28 by 28 image, that's 784 inputs, then pass it through layers with 100 neurons, then 300, then 10 for the final digit classification.
And the process is the same.
The same iterative process. You apply the chain rule, multiplying Jacobians, working back from layer 3 through layer 2, all the way to layer 1. The computation doesn't suddenly explode just because you added more layers. That's the magic. That's why deep learning works.
Okay, now what about those intermediate layers? They often have activation functions like ReLU. How does the Jacobian of those functions fit into the picture?
Good question. So for intermediate layers, the activation function usually applies a single univariate function, meaning the same simple function to each element of its input vector independently. The most common one today is ReLU, the rectified linear unit, fx equals max 0x.
Right, it just outputs the input if it's positive and 0 otherwise.
Exactly. Now, when you calculate the Jacobian of a function like that, where it acts element-wise, you get a really nice result, a diagonal matrix.
Meaning zeros everywhere except the main diagonal.
Correct. And each element on that diagonal is simply the derivative of that simple univariate function, like ReLU's derivative, evaluated at the corresponding input element.
And what's a practical impact of that, especially for ReLU?
Well, the derivative of ReLU is just 1 for positive inputs and 0 for 0 or negative inputs. So that diagonal Jacobian matrix for ReLU, it contains only zeros and ones.
And multiplying by a matrix full of zeros and ones.
Greatly decreases computation, as the paper says. It effectively zeroes out entire rows or columns in the subsequent matrix multiplications, essentially pruning the calculation on the fly. Any neuron that outputted 0 doesn't contribute to the gradient further back.
Wow. So that's not just mathematically neat. It's a huge efficiency win in practice. It helps speed things up dramatically.
Hugely. It hints at why things like sparse optimization can be effective in DNNs, too. It's one of those subtle but critical details.
Okay, so, up until now, we've mostly talked about fully connected networks, where every neuron connects to every neuron in the next layer, maybe with an activation like ReLU. But what about convolutional neural networks, CNNs? They use those convolution operations. That seems like a totally different kind of calculation, doesn't it?
It really does seem different on the surface.
How does backpropagation handle convolutions? Can you remind us quickly what a 2D convolution is?
Sure. So imagine your 2D input, like an image. You have a smaller matrix called a filter or kernel. You basically slide this kernel across the image, position by position. At each position, you do an element-wise multiplication between the kernel and the patch of the image it's currently covering, and then you sum up all those products. That sum becomes a single value in your output feature map.
Right, and the feature map highlights patterns the kernel was designed to detect. The stride, how much you slide the kernel each time, and the kernel size affect the output size.
Exactly. So the challenge is, how do you fit the sliding, multiplying, and summing operation into our nice, clean framework of Jacobians and the chain rule, which seems built for matrix multiplication?
Yeah, it doesn't immediately look like WX plus B.
It doesn't. But here's the key insight, which the paper states as lemma 2. A convolution operation can actually be represented as a matrix multiplication.
Really, how?
There's a way to take the filter, the kernel, and rearrange its elements into a much larger, specially structured matrix. The paper calls it a Toeplitz matrix formed from the kernel. It's structured in a way that when you multiply it by the flattened input image patch, it performs exactly the same calculation as the sliding convolution.
Whoa. Okay, so you can basically unroll or reformat the convolution into one big matrix multiplication.
Essentially, yes. It mathematically proves that xk, input convolved with kernel, is equivalent to t up k vec xt, a specific tuplets matrix times the vectorized input.
That's the aha moment then. If you can express convolution as matrix multiplication.
Then lemma 3 follows. A whole convolutional layer, which might have multiple filters and biases, x kin plus bi, can be equivalently expressed in that familiar linear layer form, ytx plus bi. The big weight matrix W is constructed from those tuplets matrices of the filters.
So for the purpose of calculating gradients via backpropagation, we can effectively convert a convolutional neural network to a typical fully connected one, mathematically speaking.
Exactly right. It brings CNNs under the same unified backpropagation framework. Despite their unique spatial operations, the gradient calculation can still leverage the chain rule and matrix multiplications just with these specially constructed matrices. It's quite elegant.
That is really clever. So stepping back for the big picture view from the paper's conclusion, they really managed to show how to simplify gradient calculation in all sorts of DNNs using this Jacobian operator and matrix-based backpropagation.
They did. They offer clear insights like how that single-layer gradient calculation acts as a model for the final layer of any DNN. And, crucially, as we just discussed, they showed how these complex-looking CNN layers can be mathematically transformed into equivalent linear layers for the gradient computation.
And these aren't just theoretical points, are they? The paper suggests this understanding has practical applications.
Yes, they point out these results can aid research in important areas like compressing DNNs, making models smaller, faster, more deployable on edge devices, for instance, and also in sparse optimization, finding ways to train and run networks more efficiently, perhaps using algorithms like iterative hard thresholding they mentioned.
And throughout it all, what really stands out is that commitment to clarity, the goal of concise mathematical justifications to make these results clear and useful for people from different fields, even without deep math backgrounds. That's really valuable.
Absolutely. Making complex ideas accessible is key. And they're not stopping there. Looking ahead, the authors mention plans to extend this Jacobian-based analysis to other important network architectures, residual networks, recurrent ones, LSTMs, even transformers, and also looking at components like batch normalization.
So the quest for deeper understanding and efficiency in AI definitely continues.
Always.
Okay, so we've taken quite a journey today. We started with that feeling of AI magic, and we've peered into the engine room to see the core mechanism that makes it learn, backpropagation.
We saw how this algorithm, using tools like Jacobian matrices and the chain rule, elegantly and efficiently tackles that really complex problem of gradient calculation.
Even for advanced structures like convolutional layers. Hopefully, you now have a deeper appreciation for the sophisticated math calculus and linear algebra, really powering the AI you interact with daily. It's not magic, but actually very clever, iterative computation.
And that understanding is genuinely empowering, isn't it? It means you're moving beyond just seeing the output of a black box and starting to grasp the how and why behind these systems' ability to adapt and improve.
Absolutely. You know, the paper's conclusion mentioning exploring new network types, that got me thinking. Given that backpropagation or something very like it is this fundamental learning mechanism, what kinds of breakthroughs might we see when these core principles of gradient calculation get applied to totally new AI designs? Maybe ones we haven't even conceived of yet.
That's a fascinating question.
What untapped potential still lies hidden in really understanding the mechanics, the how, behind AI's learning? It's definitely something to ponder until our next deep dive.